Great, can you all hear me okay? Thumbs up? Nice. Thank you, Rana, that was really nice, and thanks for the opportunity to be here today. It's pretty amazing to be here, actually. My first scientific conference was ASLO in Victoria, and that was, I think, 16 years ago, so it's fun to think about how time goes on. So I want to start by acknowledging that we're on the traditional territories of the Coast Salish people. And as Rana mentioned, I lead the Salmon Watersheds lab at Simon Fraser University. This is the group, and it's a great group of postdocs and grad students and undergrads, and we work on trying to understand how these systems function and try to use that information for effective management. And so I'm going to talk a little bit about some of our work today. So I want to start by taking you underwater. So rivers are defined by their connections, and if we go underwater, we'll feel those connections. The water will be flowing by from a melted snow or rain that fell upstream. And if you're lucky, salmon will be swimming by as well on a journey that might be thousands of kilometers long from the ocean back home. And so today I'll be talking about those connections and what they mean in terms of how these systems work and how we live in them. So I grew up in this type of ecosystem. I grew up in Oregon. This is a picture of my family. We spent a lot of time along the banks of rivers with salmon. Here's my dad with a sweet mustache and me with a sweet bowl cut. I actually remember the bowl being on my head and then getting the trim. But this was really foundational, I think, in terms of me thinking, really falling in love with these rivers that salmon call home. And now I feel fortunate to live in British Columbia. This is my daughter, so my wife, daughter, and I live here. And this is a picture of my daughter with some salmon in the background. And this picture means a lot to me, and it makes me think a lot about the work I do. And accordingly, one of the things I think a lot about is about the ability of Earth's systems to attenuate or absorb or cope with change, and how that capacity, that resilience, how we manage for it. So for example, Dr. Katie Arkema mapped out the ability of landscapes like coastal marshes and mangroves to deal with storm surges and sea level rise over the future 50 or 100 years. And what they found is that these systems, if they're protected, will protect 50% of vulnerable people from this global change. And I think this is important for two main reasons, urgently important for two main reasons. The first is because perturbations are increasing, the severity and the magnitude of these sort of climate drivers are increasing. And then secondly, at the same time, there is this degradation of these same habitats that do provide these natural defense systems. So here are some of those coastal marshes as they're getting dammed or diked, I guess, in this case. And if we're thinking about risk, we should, of course, think about the different components of what makes something or a group of people vulnerable to environmental degradation. So a simplifying construct is this exposure plus sensitivity leads to vulnerability. So for example, the CDC in Georgia in the southeast United States mapped out the vulnerability of people to heat-related disease or death. And so to do that, what they did is they simply mapped out heat exposure, the number of days when it's too hot, and then the sensitivity of different people to dealing with that heat exposure, whether or not they could economically afford an air conditioner, probably. And collectively, the product of those two things leads to the vulnerability. And so I think in society these days, the ideas of environmental risk are deeply intertwined with ideas of social justice as well. In the places where I work, along coastal BC, one of the groups of people that might be particularly vulnerable to environmental change are indigenous peoples or First Nations. And so if we think about this equation in light of some of their communities, we could imagine that some of the First Nations communities that do rely really strongly on natural resources like salmon For example, some BC communities eat salmon 47 days a year, a recent study found, and those salmon comprise over 50% of their annual intake of some of the vitamins that people need. So you can imagine that if salmon populations decline, they would have high exposure to that. And indigenous peoples in some communities also, might not be as economically able to cope with that change. And indeed, across Canada, indigenous communities, indigenous peoples are twice as likely to be unemployed compared to other people. So collectively, this might lead us to, being really concerned about the vulnerability of, in this case, indigenous peoples to some of these environmental risks. Indeed, I think it was 41% of households in BC that were indigenous reported concerns about food insecurity. And so across the world, even though the UN Declaration on the Rights of Indigenous People does mandate that indigenous people have this fundamental human right to protect and steward their environments, increasingly, they're at this intersection of development and risk and social justice. And I think as scientists, it's important for us to ask these hard questions. What role is science, or sometimes pseudoscience, playing in these challenges of environmental degradation and social justice? And an indigenous scholar from New Zealand, a Maori author, wrote that science has played a dark role sometimes, and it is implicated in some of the worst excesses of colonialism, is a quote from one of her books. And so that's the social the social background for the work that we do. Honestly, I'm just a salmon guy. I love salmon. I love rivers. But I increasingly think about the cultural fabric and the sort of cultural landscapes that we work in. And the fact is that the places where we work have been managed for hundreds, if not thousands of years. So this is what I really think and love to think about our salmon. Salmon have this amazing life cycle, so they go from where they're born in fresh waters. They might grow for a couple years before they head out to the sea. When they head out to the sea, they're probably the size of a small hot dog or so. And then they'll go to the ocean and grow big, up to the size of a wiener dog or Rottweiler, depending on the species and the year. So the bottom line, though, is that they have this amazing migration that connects headwaters to the ocean and then back again. And so salmon do make rivers flow upstream, and their migrations are hundreds, if not thousands, of kilometers long. And so you have these connections. And these connections also aren't just fish, they are the flows of water as well. So here we are in Victoria, down on the southwest side of Canada. Here's a map of Canada defined simply by its fresh waters. So Canada is a real water nation, has the longest coastline in the world, lots of lakes, lots of rivers. And you can imagine that these flows of water and migrations of fish connect these landscapes. So today I'm going to be talking about those connections. I'm going to be talking about, first of all, what they mean for the way that these river systems function, how they work. And I'm going to put forth the idea that they create this emergent property of stability and resilience. And then the second part of the talk is going to be pretty different, and it's going to talk about how our work was at a challenging intersection of environmental decision making associated with indigenous rights, environmental risk, and industry development. So first of all, how does river structure and connectivity influence resilience? And today, when I talk about resilience, I mean the ability of a system to absorb or dampen a perturbation. So first of all, rivers have this amazing structure, a fractal property. Most rivers branch a lot, and so the more you look, the more branches you see. Tiny creeks will form streams, streams will form rivers, rivers will form large rivers. So here you can see this crazy fractal dendritic network of the Yukon River, and then a river network that was grown mathematically by one of my postdocs, Justin Yackel. And so you can have these fractal properties that actually describe the laws that many rivers seem to follow. So I want to sort of posit that these properties, this structure is really potentially foundational for the way that river systems work. So the idea is that if you have a red river and a blue river and they come together through this coalescence, through this joining of tributaries, the downstream river will be purple. Okay, maybe not purple. This is more realistic. So here's just east of here, this is the Fraser River getting joined by the Thompson River, and you have this sort of latte-colored river joined by a coffee-colored river, and downstream is like a frappe latte-colored river. But this idea of aggregation and assimilation probably doesn't just apply to color, it probably applies to dynamics as well, the mixing of variability. And we also know that when you mix variability, when you bring things together that are operating differently, portfolio effects should arise. And this was postulated in the 50s by economics folks, and what they realized is that if you have asynchronous dynamics in your assets, all you, I'm sure, have amazing stock portfolios, so you have really diverse stock portfolios, and through that diversity, if one of your stocks goes down, it might be buffered by the other. So the returns will be more stable through time. So if you have this asynchronous dynamics and you can integrate across it, you should get more stable returns through time, less vulnerable to the booms or the busts, actually. Okay, so that idea could probably be applied to rivers. So rivers come together, they're integrating this variability. If that variability is asynchronous, then we should get stability, we should get resilience. So as tributaries come together, they should become more stable, all things being equal. And you should get this hierarchical downstream pattern of stability. So that's an idea that I'm excited about that we've been looking at for a couple years now. So first of all, we did some math. Postdoc Justin Yackel, this is metapopulations, but frankly, it doesn't matter. It's all about mixing variance. And what he found is that if you just plot variation, so here's a really noisy population, here's a really stable one through time, as a function of where it is in the watershed, you should have populations that are more stable towards the base of the watershed because they're integrating those asynchronous dynamics from upstream. And so we want to test this idea with some of the great, portfolios that exist in Canada's wild salmon rivers. And so that's what I've drawn here. Here's some trees of some of the rivers in BC. The Fraser River, for example, if you draw its river network and flip it up and show it against the curvature of the Earth, as I've done here, it's so big that satellites would get caught in the branches and birds would be flying down around the base. So there are these huge connected integrators. You can imagine these portfolios be remarkably diverse. So we compiled data on a suite of different dynamics. Here, let's talk about hydrology, river flow. And so these are different sites within the Fraser River, this catchment that's the size of the United Kingdom. And what I've plotted here is each point within this catchment and just simply the variability, the daily variance in how much water is flowing down at a given time. What we see is that the stability of the whole catchment is twice as great on average as the smaller catchments. So we see a pattern that's consistent with this idea. This has been documented before, but it's exciting to see in relation to this idea. And this is actually kind of a big deal. If you look at how stable these flows are, the whole Fraser has only had one really big flood that killed people and caused millions of dollars of damage over the last 40 years. If we use that relative magnitude of event, that happens in small catchments about once a week on average. So the flip side of that is that if rivers didn't have this property, Vancouver probably wouldn't exist. It would just be wiped off the face of the earth from this crazy power, this loss of stability. And I think human societies have kind of taken, we've benefited immensely from this unrealized power of river systems. What about resilience to other sort of patterns or scales of change? So that was just sort of short-term stability. What about resilience to longer-term change? So here the idea is that if we think about how water flows through time might be changing, we predict that with global warming, we'd see that most of the snowmelt would be coming down earlier. So we'd predict you go from this sort of blue hydrograph curve towards this red one. Snowmelt's getting earlier as the world warms. But we might predict that in some catchments, if it's north-facing maybe, or maybe if it has a glacier, then it might be getting later. But as you integrate that local climate signal, that might get smoothed out. So that's the idea here. That was tested by PhD student Kyle, and this paper came out last year. And what's that? This is sort of the key result point shown here. So what we see is that each point, again, is a place in the Fraser River. And so on that side of the axis are small catchments. On this side is that huge, amazing climate portfolio of the whole river system. So in small catchments, what we see is that indeed many sites are warming rapidly and the snowmelt is happening earlier, but actually some sites have the opposite. And so there's a huge local range in the sort of long-term change in hydrological response in the system. But as you go downstream, as those different climate signals are brought together, they're attenuated, and by the time you get to the Fraser whole system, whole main stem, what you see is there's actually not much change, but then 95% of the variance in that local change has been lost. And shown in yellow are simply null model runs to show that this is not a random thing. Okay, so what about other properties? That idea that rivers act as portfolios could apply to a bunch of different processes or properties that happen in rivers. And so one of our master's students, Holly, looked at this in relation to First Nations fisheries that happen throughout the watershed. So again, the prediction here is that at the base of the watershed, the fisheries there would be encountering incredible diversity of salmon runs. All these different locally adapted salmon populations swimming by, those might be quite stable from year to year. Whereas up in the headwaters, lower salmon biodiversity, maybe more booms and busts in those fisheries. Some of these results are shown here. Indeed, this is for Chinook salmon. The variation from year to year in terms of the fishery was 4 times higher in the small catchments compared to the low catchments. In other words, the fisheries that integrate over greater salmon biodiversity have much more stable catches over time. And this also operated in terms of fishing season length. So the fishing season length was 5 weeks in the headwater systems, where they'd only target one run timing group that came back, whereas at the base, they'd have fresh fish on the table for upwards of 5 months a year. In response to these papers, Grand Chief Bob Chamberlain said, "Protection of the broadest genetic diversity of wild salmon stocks will help them provide for our future generations a component of our constitutionally protected Aboriginal rights." So I think what Chief Chamberlain is saying here is that in order to benefit from this diversity, you need to protect those pieces. And then in response to this paper, Finn Donnelly, member of Parliament, said, what it shows is the need for government to embrace a watershed or whole systems approach in decision making. And this feeds into the next section of this talk. So the first part of the talk, what I hope I did is shown some data that puts forth this idea that rivers might have this emergent property of resilience and stability that could apply to a bunch of their different dynamics or properties, from flows to fisheries. And I think this is actually a natural defense system that provides enormous benefit to people, economics, as well as cultures. All right, so now I'm going to transition to the second part of the talk, and quite a bit different, but talk about how our work was at the sort of part of a challenging environmental decision-making process. So here the idea is that these same connections, the connections that can potentially drive emergent stability, could have the sort of also corresponding effect such that risks could get propagated by these same connections. So, for example, if you have a habitat at the base of a watershed that all these migratory salmon use, if the habitat's altered, the risks could get spread upstream as well. And for this work, we're working up in the Skeena River. This is the second most productive salmon watershed in Canada. Again, here it is on tree form. This one integrates it integrates an area that's the size of Switzerland. And this is really where we've been working, right where the river meets the sea. So the Skeena River is coming in on the right side, upper right side, and you can see that muddy water coming in and meeting with that sort of gray-green water of the Pacific Ocean. And then right where it meets is this habitat called Flora Bank. And Flora Bank houses the largest eelgrass bed of the greater Skeena Estuary. And just to give a little bit more background about the salmon life cycle, so again, salmon connect freshwaters to the ocean, but in between is this estuary phase. And there's increasing evidence that some populations seem to really rely on this estuary phase for a nursery sort of part of their life, where they make this difficult transition from freshwater to the ocean, grow a little bit more, and then keep their journey going. It's sort of like the puberty of the salmon life because they're trying to cope with different changes, awkward. And work has found that what happens in estuaries can have population level consequences. So studies have compared estuaries that are more altered compared to the ones that are pristine. And what they find is that in general, salmon populations are less productive in those estuaries that have been highly altered. At this location, a foreign fossil fuel company supported by Proponent, which is the most lucrative company in Asia, put forth this proposed development. This is for a large liquid natural gas terminal that would take gas from the fracking fields of northeastern BC to tankers for overseas market. For scale, each one of these ships is about 1,000 feet long, and this would be one of the biggest, if not the biggest, LNG terminal in the world. And the stakes were high. So right off the bat, this company offered the First Nation that I work with $1 billion. They said no. In Canada, the way that a decision like this is made is through an environmental assessment process. And so a company will come forward, and what they'll do is they'll create an environmental impact statement that assesses the risks in theory, and then that'll form the scientific basis of a decision, which will then be implemented and evaluated. And so in Canada also, the impact statement is funded by the proponent, so by Pacific Northwest LNG, by Proponent, and so they hire private consultants to create this document. And so I read this document. Many people read this document. It was actually, I think, 9,000 pages long, and we had 30 days to comment on it. But there's a couple things that caught my eye from a science perspective and raised some concerns. The first was this statement said that the area was of low importance to salmon. They said that salmon do not use floor bank eelgrass habitat for nursery habitat or other life-dependent processes. This surprised me for two reasons. First of all, there's a lot of work suggesting that eelgrass habitats in general are important for salmon, and this was the biggest eelgrass habitat in the area, and it also was right where the ocean hits the sea, right where those young fish are going to be. And then secondly, there was a study 40 years ago by DFO that found that this actually was quite an important salmon habitat. So that statement was scientifically worrisome. And the second part was that they stated that the project impacts would be local, that there wouldn't be risks posed to upriver First Nations. They shouldn't be given a place at the decision-making table. They concluded that the project posed no significant risks to salmon. So what we did is we thought that these would be good hypotheses to test, that these would be good to provide data and see if they are supported or not. And so over years we did that. It was a multi-step process, but this was really led by my grad student Charmaine Carr-Harris. She was born in Prince Rupert, right where this terminal is proposed, and she grew up, in this case, looking at fish, but I'm sure eating fish as well. And so she created this amazing collaboration, involved multiple grad students, and it was in collaboration with the local First Nations on whose territory this project was proposed. And so it was the Loch Lom's First Nation. I should note that I'm speaking as a scientist. I'm not speaking on anybody's behalf, so I just want to be careful with that. But this is, frankly, one of the most rewarding collaborations I've ever been a part of. It was amazing to be out on the boats. Pretty big science, big purse seines, waves hitting you, smell of seaweed, fish everywhere, working with folks that knew the area so well. What we found was that there were fish there. There was fish everywhere, not surprisingly, because it is the estuary of a really important salmon watershed. But what we found is that this particular area where this project was proposed contained 25 times more salmon than other areas. to actually show some data. Those are mapped out here. Each one of these points that you can see here is a different location that we sampled. We sampled systematically for several years during spring and summer across all these 26 locations. We caught salmon everywhere, but these points are scaled to the average abundance of fish during the summer. And what kept on coming out was this place right where this project was proposed, shown blown up here, seemed like it just consistently had the most fish. The second thing we did is we tried to ask this question of, well, where are the fish from? Are these project effects local? And so we use genetic analyses. Salmon are locally adapted, and so you can actually ask them sort of where they're from. So you take a fin clip, and then that's matched with the population of origin. So maybe the fish is from the Babine River, 400 kilometers upstream, or maybe it's from Kitwanga, 75 kilometers upstream. And I think this is important because if you drive up the watershed, this is the kind of thing you see. You see people fishing, and you see communities fishing in places where they've literally fished for thousands and thousands, many thousands of years. And so trying to understand whether a project such as this poses risks to upriver communities, I think is important from a social equity type of question. What we discovered was that if you look at where we sampled at the origin here in this proposed project location, the fish we caught were from throughout the watershed. So the line indicates where those fish were coming from and where they were going to. The red lines are sockeye salmon, the blue lines are Chinook salmon, the two most important food fisheries, and also the two for which genetic baselines are well established. And so what we found is that the fish there, we conservatively have evidence now that they're coming from throughout the watershed as well as beyond. There's actually some fish using it from adjacent watersheds as well. But over 50 populations of salmon use this flora bank habitat on their way out to the ocean. These fish come from over 10 different First Nations territories. So we worked with different First Nations groups in the watershed, and we published that paper with the fisheries scientists from throughout this area. Here's some of their flags here. So this is more than twice as many First Nations as were involved in the environmental assessment process. What this did is it provided data, provided evidence that indeed fish swim upstream. Not surprising, but what it demonstrates is that those risks spread upstream as far as salmon can swim. So if we go back to this environmental assessment report, the data didn't support these statements. Indeed, it kind of supported the opposite, that it wasn't just that this was sort of typical habitat. This seemed like it was the most important habitat in the whole area. And then secondly, the project risks would spread upstream as far as salmon can swim. So these findings were submitted as evidence in these narrow policy windows, and indeed they did shift the environmental assessment some. The bottom line was that they kept saying that the project posed no risks to salmon or people that relied on salmon. And I kind of thought that the decision makers would be psyched to get these data. So this is a cartoon. This is a cartoon I drew when I was processing all this. I was like, why isn't it that I can just hand them my papers and they'd be like, yeah, nice job, thanks. This is great, awesome work. But in general, that's not the response we got. It was pretty much silence. So we worked hard. We wanted to make sure that people were aware of what we were finding, so our work was covered across Canada and internationally as well. And we also got the opportunity to speak with communities for whom this project might pose risks to. And I even bought a suit and got a little haircut, not a big hair, but a little haircut, and went with First Nations chiefs to Ottawa, Canada's capital, to talk with decision makers. And I talked about what the science was showing, and the First Nations leaders talked about their concerns about what that meant for their communities. And then the project was approved. And the thing that they said that caught my attention was that the decision was based on science and traditional knowledge of indigenous peoples. And so again, this makes me really think about what role does science, or the scientific enterprise play in issues of social equity. And I think in Canada, many authors, many people have suggested that some environmental assessment reports that are paid for by the proponent are, a thin veneer of pseudoscience that allow groups to justify a project going forward. And this project in particular was, that decision got attention, and it, as well as other ones, really got people concerned about decision-making processes in Canada, and the federal government is indeed looking at trying to strengthen those these days. So the project got got approved, but it hadn't been built yet. And over time, there was more and more protests camps. So this is a group of First Nations leaders that built a couple cabins on Lilu Island, which is where that project would get built. One of the chiefs told me, I wouldn't be here without your science. That was generous of him. I'm not sure that's true, but I think it does show the value of connecting with people. And prices kept on going down for gas as well. And the project kept on having to get changed. And ultimately, the project was canceled this last fall. And then later in the fall, I got invited to go up to a totem pole raising ceremony on Lilu Island, the site of this location. And this is the wolf crest. It's a symbol of the Gitwal clan, which is whose territory this project would happen on. And it was honestly a pretty amazing event. I felt honored to be there, and it was so cool just be holding these ropes with First Nations chiefs or fishermen or some little kid, white folks, indigenous people, and everybody just coming together from throughout the watershed and literally pulling up this symbol of protection. And there it stands now. And to me, this really it's made me really think about how watersheds, they don't just connect, water flows and fish, but they connect people as well. And they also really got me thinking about, how, risks can spread through migrations of fish, but environmental stewardship can spread as well. And so protection of this one habitat can actually pay dividends for people who live throughout the watershed. Okay, so today I talked about watershed connections. I talked about how water flows and migrations of fish matter. And honestly, I'm a little self-conscious about this talk because fundamentally it's based on really kind of simple things. It's like fish swim upstream and water flows downstream. And giving that to this audience, it's like, oh, great, nice job. But I actually think that the implications that those connections and that integration are pretty fundamentally important. And I think we're just sort of wrapping our heads around the way that they control these systems work and how we should live in these systems. So I have three main take-home points. I believe that free-flowing rivers do have this natural defense system against perturbations. Secondly, I think there is this amazing need to align decision-making with the scales of these natural connections, thinking about this risk propagation and this stewardship propagation. And I also think a lot these days about how we are doing science and what our role in this time is as scientists. And what I find really valuable and impactful is collaboration and co-development, and really thinking about the cultures that live in these landscapes in which we work. And seeing one of my grad students getting a chance to work with one of the fisheries scientists from Loch Lom's and seeing him hold this young fish and collecting data together, and that data hopefully can inform effective stewardship of this salmon, which have been foundational to their cultures and hopefully foundational to their futures as well. I don't know, there's something I feel like it's really a powerful approach that has been exciting for us. And so we're trying to do more of this type of work. For example, on the Central Coast, one of my grad students, Will Atlas, has led a project where they're using, collaboratively with the Heiltsuk Nation and support from Hackeye Initiative, they're using split cedar and peeled alder for traditional weirs. And those weirs, they're now using to tag fish and figure out their life histories and migrations. But these are the same weirs, the same technology that have been used for millennia for indigenous people to harvest and manage these salmon. And these are also the same weirs that the Canadian government banned and ripped out of the water in their movement to colonize the fishery. So now I think it's this powerful symbol of, collaborative, new visioning, old visioning too. It's sort of like this new way that for me is a really important symbol as well as an effective tool. And in general, I guess this is the way I think about collaboration and co-development these days. I think sometimes science can be imposed on a place and on a people, and I think through working closely and collaboratively, science can more arise out of a place through collaboration. And it's been super exciting in this meeting as well as everywhere to see how there's different groups doing this in different ways, and there's groups doing this way better than us, way more effectively, and it's exciting to see. So I want to end by taking you back underwater again. And this moment actually meant a lot to me. So I was working with a videographer, and we were at the base of a waterfalls, and he's like, "Come on in, this is the most amazing thing I've ever seen." And so I put on a dry suit, put on the hood, mask, crept in, tried not to die, because it was literally like right near waterfalls. But it was so beautiful. And you get underwater, and the ice cream headache goes away, and the bubbles are tickling your face like, I don't know, baby fingers, and the salmon are just sort of dancing around you, and it was so beautiful. And it made me really feel like I was a part of something bigger. And I think that's what watersheds are, is they do connect us to other people, and they do connect us to the world around us. And it made me think about a couple things. It made me think about my daughter, and it made me think about the role that I play in this world. And so honestly, I think it's inspiring and it's motivating. We have work to do. We have work to understand the resilience of these systems and how to live and operate with that resilience, and then do that hard work of science and transforming that science to inform and inspire effective environmental stewardship in this connected world. Thank you.